to our Inspiring Science Education webinar this afternoon. My name is Sally Reynolds, and it really is my pleasure this afternoon to welcome you to our very special webinar on the NASA Kepler mission, which is going to be led by Alan Gould from UC Berkeley in the States. And we really are very honoured to have Alan join us because he has more than 40 years of experience developing and presenting hands-on science activities. So he has lots and lots of information to share with us this afternoon. And he's been co-investigator for education and public outreach for the NASA Kepler mission since 2000. So lots to share with us today. Before we get started with Alan, I just want to remind you briefly about the ISE, the Inspiring Science Education project that is supporting this series of webinars. This is our portal and website where you will find lots and lots of information, resources, materials that you can use in your science teaching. We're also currently running a survey, which I'll remind you at the end of this webinar about, and we will be looking for your input to help us to improve the ISE offer. Just to let you know that joining us this afternoon, as well as teachers who are in different parts of Europe, we also have a group in Greece with Rosa Doran. So hi Rosa and everybody in Greece. Big group of teachers, 70 teachers taking part in the ISE summer school. So you're particularly welcome. And I know we have several other groups watching us in different parts of Europe as well too. So thank you very much. Please, you are very welcome to put comments, questions into the chat box. You can see that my colleague Alberto has been putting in links into the chat box. That's where you put your questions and questions you'd like to raise to Alan. And we'll also have Rosa joining us a little bit later on, and she's going to tell us about a scenario specifically related to the Kepler mission. So without further ado, I'll switch off my camera and mic and leave you in the very capable hands of Alan Gould. Alan, over to you.
Thank you, Sally, and good morning. Good evening, good morning, or whatever time it is where you are. Greetings from Berkeley, California. I've been the co-investigator on the Kepler mission for actually when it started in the year 2000, and they were building the spacecraft. And we prepared a bunch of education activities that are related to the Kepler mission. It's kind of interesting. Recently, if you have tuned into NASA lately, like for instance the Jupiter mission that just arrived at Jupiter, Juno, I checked their website and there doesn't seem to be an education component to the website. That's because the education structure has changed at NASA, and so the missions do not have education funding anymore, but there is education funding for NASA as a whole. Now, the Kepler mission basically has a very simple goal of finding Earth-sized planets in the habitable zone of Sun-like stars. And let's just take that apart a little bit. What do we mean by Earth-sized planet and Sun-like star? In this picture, you can see the Earth superimposed on an image of the Sun. Gives you the flavor of the size of planet that we're looking for. That's an Earth-sized planet in relation to a Sun-sized star. And it's sort of a daunting task in order to try to find planets that are that size around stars that are, I mean, Sun is a dwarf star, but it's still pretty big compared to the Earth. And then the other term that we used in that opening slide in the goal is habitable zone. And for a habitable zone, I see this slide, okay. We have the distance from the star being the critical factor. Well, not just distance, but the temperature of the star, which is related to the size of the star usually. So the hotter stars, which in this case is indicated as blue, the blue hotter stars. Actually, hotter stars are blue. The habitable zone, which is the green in this image, is farther out than a Sun-like star, which is shown in the middle level, and then that's a farther out habitable zone than the cooler stars. those cooler stars actually were not ones that originally the Kepler mission was looking for. They were originally looking only at, only for sun-like stars with a few cooler stars, M dwarf stars in there. But it turns out that's a very important population, because most of the stars in our galaxy are those really small dwarf stars, and those have close-in habitable zones. So you'll see later why it's easier to find planets around those kinds of stars. Now, what is this? Okay, I was going to set up a poll, but those of you who have access to chat, I invite you to type in the chat what you think this is. Okay, this is an experiment that I'm doing to see if the chat actually works as a okay, we're starting to get answers now. Okay, I get a planet transit, Mercury on a sun background, Venus transit. Okay, these are good. It turns out that actually is a Venus transit, and I forget which one. It might be 2006. But you can see the size of Venus against the Sun, and that also is not quite even though Venus is about the same size planet as the Earth, the transit of Earth across this, if we were not on Earth, if we were much farther away, transit of Earth would look probably a bit smaller. It depends a little bit on the distance that you are from the star. In fact, it depends everything on the distance you are from the star. But the star being the Sun in this case. But if you're dealing with stars that are outside our solar system, the distance is not so much a factor. It would look the same no matter how far away you are after a certain distance. Now what I'd like to do is show a few short videos about some models. It's all well and good if you're teaching about transits. And a transit, just to get it out of the way as a definition, a transit is when an object goes in front of another object. In the case of astronomy, it's usually a planet in front of a star or a moon in front of a planet. That's what the definition of a transit. But it's a good idea to give students a better concept of what a transit is by using models. So I want to switch over, Alberto, if you can change to the first movie. I want to show a movie of some simple models. I prepared a couple of short movies. Now, these are from webinars that were done for, two webinars that were done for the International Year of Light. But I took very short clips from those. I'll give you the links to the full-blown webinars later on. But here's the first one.
Is with a star, with some kind of ball, doesn't have to be styrofoam, tennis ball, whatever, and a bead. Okay, and I've put this bead on a stick. And so one way to illustrate a transit is to simply move the bead around the ball. Okay, of course the ball represents a star, and the bead represents a planet. Okay. So that's your very low-tech way of illustrating what a transit is. Whenever the ball goes in front of the star, that is a transit. Flashlight and ram it into your styrofoam ball, and then turn it on, and it gives you a nice lit star. Okay, and then you can do your same kind of, and you can mount it if you want to get really fancy, and then you can do your demonstration that way. Or you can get even fancier. I'm going degrees of fanciness here. You can make a sort of a wire. This is a wire thing that's like a kind of like an egg beater type thing. It's just shaped like this, so that if I hold that, it's very easy to make a ball go around something. So I have another flashlight here that is a lit sun or a star, and then we can make that rotate around the star. Okay. Now, One thing that's really important to realize when we're talking about the NASA Kepler mission is that we're looking at stars, and it really makes a huge difference how we look at them. Okay, so if you have a star with a planet going around this way, are we seeing a transit? Does the planet go directly in front of the star? Well, no, it doesn't. Okay. And then if we hold it this way, is the planet going in front of the star? No. Okay. So it really depends critically. There's only one special way, or a very narrow range of orientations where the planet actually does go in front of the star. Okay, so that's what we're looking for, is the transits, and there's only a certain number of stars that will actually have that condition with planets going around.
Oops, I just cut that off, but it was pretty near the end. And Alberto, if you can load the next one. The next level of sophistication is a mechanical orrery, what we call an orrery, which is a model of the solar system. And for that we have created there's a commercially available one that I want to show you a little movie of, and I'll give you the links again on the website later for where these are available.
What I like to do in a classroom is to hold it in a way and have the students raise their hands if they actually see a transit. Okay, so if you hold it vertically, there's only two or three students who would actually see that, depending on where they're sitting. But if you hold it horizontally, then the whole class would probably see a transit. This particular model also has an extra planet on it. Okay, so this is a two-planet model. Okay, and they go around at different speeds.
Okay, don't change the video, because this still image I want to refer to. In the upper right you see a cylindrical looking thing. That's a light sensor. And so this particular model is called it was developed for the Full Option Science System, which is a curriculum project at the University of California, Berkeley, Lawrence Hall of Science. And this is available for purchase by a commercial company. And I can give you the link for that later. But that if you point a light sensor at the light bulb, then you can actually get what we call light curves. And I'm going to get into that in just a minute. But let's load up the next movie, and that will show just one more kind of model that you can have. And this was actually the first model, well, not the very first model that we made, but one of the first models.
And it's adapted so that you can actually put a star right here, and out of the Lego you can turn the crank and have the model go around. And you can see that there are 3 planets here. Okay. So that's a 3-planet model. There's instructions for how to build one of these on the Kepler website too.
So that's kind of an amazing model. That a little history on that is we were trying to get a tabletop orrery model set up, and I went to our exhibits department person, who I heard had a particular love of Lego, and asked him if he could make such a model, and he said, "Oh, I'd love to if you've got some money to pay me to do it." And we did have money from the Kepler mission, so he put together the first version of this model. It was a dream job for him. But we took it to some astronomy conferences, and all the grad students and professors came by our booth, and they just wanted one. So we put the instructions up on the website. Okay, so in the FOSS model, there was the option of putting a light sensor on, and those light sensors cost they cost a fair $50, $100. We were typically using a vernier light sensor, but we decided to make a free one available on the Kepler website, and it's called Light Grapher. So if we load up the next video, I can show you how Light Grapher works. Okay, this is about these are very short videos. This one's about 2 minutes.
Alan, just before we do that,
sorry.
would you mind switching would you mind switching off your mic when the videos are playing, because we're getting a bit of feedback with the sound from the video as well. So if you switch off your mic when the videos are playing, we should get rid of that. Thank you.
Will do. Okay.
Okay, you can download it with this link right here, or we can run it right off the computer. So I'm gonna try running right off the computer. I'm going to use the built-in camera that we have, and it's going to use the camera. It should get a picture of me here now. Okay, there we go. And actually, let's use the Foss orrery. Let's see if we can set it up with the Foss orrery. Okay, the trick for doing this is to get the camera centered on the star. Okay, I'm going to turn the star on. Okay, and get the star in the center, and you can adjust the scale so that that black circle is just on the star. So that you only have light coming from the star. Okay, once you have that set, then we can start capturing data. Okay, now the reason I'm showing you this is because that classroom light sensor I showed you before, that costs $50 or $100 if you count the interfacing. But this software that you're looking at right now is free on the Kepler website. So if I press the Capture Data button, let's see what happens. Okay, so now we have a, if I rotate the planets going around, I am now rotating the planets going around, and you can see what's happening to the data that's being collected, which is light sensor data. Okay, every time the planet goes in front of the star, we have a drop in brightness, and that's what we call a light curve. So here.
Okay, so leave that image up for a second. This is a great way to introduce light curves to students, and it's a dramatic. Actually, even fairly young students who are just starting to learn about graphing, this is a great thing to have that model in front of them, an actual physical model of something, and to have the light curve generated right beside it on a computer screen. It's extremely effective for understanding what graphs are all about, actually, and then light curves in particular. So okay, so the next thing is if we can load up the second of 3 PowerPoints. I'll continue with. Oops, what happened? Okay, back to the beginning. Okay, so this is part B. I want to talk about the activity, classroom activity, which is called Transit Tracks. This is one that's up on the Kepler website. And let me just walk you through it in a very quick kind of way. There's my, at the end of this, if you have any questions or any time in the next few years, you can feel free to ask me by emailing me. There's my email address. And I'll also put that in the chat later. So the reason this is called Kepler Mission is because we rely heavily on Kepler's third law to determine what we can measure from those light curves is the spacing of the drops in brightness, which will give us the period of the planet. The period here is the t. And from Kepler's third law, we can calculate the average distance of the planet. Technically, it's called the semi-major axis because they're ellipses. But in general terms, we can call them the average distance from the planet. Now that simple equation, r cubed equals t squared, is Kepler's third law. But for another star, Newton's universal law of gravitation kind of enters into the picture. The bigger the star is, the more it affects the distance the planet will be from the star. So we have this mass of the star factor in that equation. Here's a graph showing our solar system. This is a linear plot, and you can see how all of the I don't know, can people see my my cursor? Probably not.
Not at the moment, no. You need to pick it up, I think, at the bottom, and then you can use it.
Oh, they didn't tell me about that.
Oh, now we have it. Yep. You see at the top?
Oh, I see.
Pointer
Okay.
here.
Pointer.
Yep. And then you're away.
Now I have a pointer. Oh, okay.
Yep,
Yeah.
you're away.
Well, amazing. Okay, so you can see all the inner planets clustered down here at the bottom. Okay, and so this is, you know, for not a particularly good plot for the inner planets, although you can expand it out. But for older kids, like high school, when they learn what a logarithm is, they can start to understand what logarithmic plots are. I would never do this with middle school or younger students, but this spreads out the planets all nicely. Okay, when you do a logarithmic plot. Now, reading a logarithmic plot is a little tricky. Like if we want to find out the relationship of the orbital period of Mars, you can read across. This is how you use graphs. You read across, and it's about, well, what is that period? It looks like it's about 1.8, and then it's actually exactly 1.88 years according to the latest data. And then we have to read down, but on a logarithmic plot it's a little hard to do. Like that, what is that reading on the logarithmic plot? It looks like about 1.7 to me or so, but in fact it's 1.5. That's an artifact of the logarithmic plot. It's hard to estimate on a logarithmic scale. So especially with younger students, we tend to use regular graphs, linear graphs, but we'll change the scale, the period in Earth years to whatever our light curve is confined to. So like if it's a 10-day period, it's within a 10-day period, we would use a graph like this. If it's 100 days, we'd use a graph like this. And if it's, I think this was in this is actual years, and those are the planets in the solar system for the inner solar system now, not the outer solar system. Okay, so essentially there's two ways that they confine the distance. Okay, the first step actually is to measure the period, that is the spacing interval of those drops in brightness of the star as the planet goes in front of the star. Now, like for instance, these are the first 4 planets that Kepler detected planets on, and first 4 stars. And the first 3 actually don't quite count. We don't count that in the actual count of Kepler discoveries because those were already discovered. Trace 2, HAT P37b and HAT P11b had already been discovered. It was very useful because they were in the field of view, and it was a good test of how the system was working. The first one that was really discovered was Kepler 4b. And if you look carefully here, what is the period that we see in this light curve? That. Anybody who's on the chat might put in their estimate of that period. Looks to me like it's about, yeah, close to 3 days. It's a little over 3 days. Let's see what. Oh, and this is what a real that light curve that I just showed. This one is based on real data, but it's not the real data. It's cleaned up so that it's easier to read. This is what a real light curve looks like. There's a lot of noise in it, and this upper one This upper one is the similar to the one that we saw before, but the actual data. And this is an expanded out showing what each of these actual dips look like when the time scale is expanded out. Okay, so we said that was 3.2 days. Now, assuming that's a sun-like star, this is a plot 3.2 days. Let's calculate what its average distance is. Okay, and this is graphically calculating. 3.2 days gives you about, what is it, 6-point-something million kilometers. Okay, and we usually will convert things to AU, the average distance of the Earth to the Sun. But in this case, we're using millions of kilometers. So what we do at this point is turn the students loose. Once they have a clear understanding of how to find the average distance from the star, we will let them use any of these graphs that they need for the particular planet that they are going to find the distance to, the distance of the planet from its star. And then we'll turn them loose with a bunch of light curves like these. Okay, and then there's 2 more sheets of light curves. Let's see if I have those. There's Kepler 5b through Kepler 8b, and then Kepler 9. Now, it's interesting when you get a star with multiple planets. Okay, this is an example of 9b and 9c. We've actually color-coded this to make it easier for the students to distinguish which is which. But, of course, the light curves coming down from the Kepler spacecraft, they don't come color-coded. So one other thing I would point out here, that's a critical thing we can find from these light curves, is the average distance of the planet from its star. But we can also tell the size of the planet, and that depends on the depth of the dip. Okay, so you can tell that this is a much bigger planet than this. Kepler 10b was the first nearly Earth-sized planet that we found. Okay, and an Earth-sized planet actually would have a drop in brightness of approximately 1/100th of 1%. A 1/100th of 1% drop in brightness. That's 1/10,000th drop in brightness. And that's one of the most incredible things about the Kepler spacecraft, is that it was designed with such exquisitely sensitive photometer, that is the light sensor, it's called a photometer, that it could detect an Earth-sized planet with 1/10,000th drop in brightness. Okay, and this Kepler 10b was the first one. It was like, it may be twice Earth size, not quite twice Earth size. So anyway, and this actually, Kepler 11 had 6 planets. So we have, for the sake of the students, to make it a little simpler for them, we've broken it out into 3 planets and 3 planets, and color-coded it at the same time. But when you look at that, when it's not color-coded, it can get pretty confusing. Like here is all of them together, and you can tell if it wasn't color-coded, it would be, well, not too hard to decipher, actually, because the depths of these transits are very, very distinct. Okay, so that's easy to figure out. So then the students would have 2 different ways, actually, of getting these 2 types of data. In this, they would be putting the orbital distance of their planet. They put the name of the planet, the period, and then the orbital distance they would get from a graphical method, one of those 3 graphs that I showed you before. To get the planet's size, it's a formula that the planet size is 10 times the square root of the drop in brightness. Now that's actually pretty straightforward math if you have a class that wants to do the math. Basically it's the, if you have the star, if you look at my image here, the star is there and the planet in front, it's the area of the star divided by the area of the planet, or vice versa. It's the area of the planet divided by the area of the star that gives this formula here. I leave it as an exercise for you to derive that. So they can figure out the average distance and the planet size. Now there's another data sheet for using the actual formula r cubed equals t squared, except that we use it with the mass of that star. If you want to get really an accurate result, you need to include the mass of the star. Now, you might ask, how do you get the mass of the star? The Kepler spacecraft doesn't give us any clue to that. The masses of the stars were determined by a huge effort of ground-based telescopes to characterize thousands, actually millions of stars in the Kepler field. And they determined the masses using very clever astronomical means that astronomers do to figure out masses of stars as best they could. And I'm not going to explain how that is right now either. But you can use that in this table. This is for older students, actually, to deal with cube roots. And then, but the planet size is calculated the same way. Okay.
Alan, could I interrupt you briefly?
Sure.
There was, I think the question probably that the EUN Science Department put has probably been answered, because they asked a little bit earlier specifically for how do you determine the distance from the Sun to the planet. So I think that's probably been that's been answered, unless they have anything further they want to ask, or you want to add to answer that question?
Well, it is Kepler's third law, which is the established relationship between the period and the average distance. It was amazing that he discovered that 400 years ago. How the heck did he do that? That's pretty amazing.
Yeah. The other question then came in via my colleague Alberto. With Kepler's law, you calculate the average distance of the planets and the stars. Is there a way to calculate also good measures for the aphelion and for perihelion?
Yes, you need to determine the eccentricity of the planet, and that can be done in the case of, by an analysis of the shapes of the light curves to some extent. Yes, you can determine the eccentricity.
And is that information available?
Yes, on the Kepler website there is a listing of all of the discoveries. Well, yeah, and all the data on the planets is listed, and many of them have eccentricities listed with them. So
okay, hope that answers that.
Yeah, I'll show you the. I'll actually show you that table in just a few minutes.
Okay.
Okay, so we are ready for another activity, which I think is very interesting, is called the Kepler Transit Hunt. So if we can load the next movie. Let's take a quick look at that. It's about a 3-minute movie, but this is a pretty cool thing. Let me start that and turn my sound off, because this doesn't have narration. In this interactive, you start out just by moving the telescope view and over the star just to get things started. Then the next screen shows you a bunch of sample stars to try out. And then the next screen shows you characteristics of the star that you select. And there's this handy-dandy note bar at the bottom where you can collect data. So we're putting the spectral type, the star mass, the star radius, and the temperature into that note bar. Then the next one is to actually collect data. So we click the start button, and every time the star blinks, the star that's in that field of view there at the top, you press the record blink button. And this is a little tricky because you have to read the instructions to know to do that, but you record the blink button and it presses those. Now a little secret is that you don't really have to wait, you don't have to do it till the very end before you start measuring the period, and you can drag the scale Notice how we drag the x-axis scale up to more easily measure that. And I'm thinking that's about 3.2 days. So we put 3.5 into the note bar there. And then we also can measure the brightness drop. It looks like it's about 0.9 something. 0.95 we'll put. And then we go to the next screen, and we have that calculation. This is the Kepler's third law again. But here, for young audiences, we can just drag. It's dependent on the period and the mass, so we drag those up from our note bar. And then we need to convert days to years, so we press that convert button. And that gives us, and then we calculate, and that's the distance, the average distance to the planet from the star. Okay, then the next screen is to figure out if it's in the habitable zone. Now here, we need to adjust the star temperature to the actual star temperature, which in this case is 6,213 Kelvin. And we also need to move the distance bar. And that's moving kind of slow, so let's just drag it, and that's where the planet is. The blue zone is the habitable zone, and I can tell right now that is not in the habitable zone. So we have to put a no in the note bar under habitable zone, that is not in the habitable zone. We go to the next one, and we could, this is an amazing thing, we can calculate the temperature of the planet using the Boltzmann's law, which depends on the star's temperature, the star's radius, and the distance of the planet. This is an interesting way to just look at how these formulas work. What are those things dependent on? And so this temperature is 1,829, and we can calculate the size of the planet like you saw before. We take the star's radius and the star's brightness drop, the square root of that, you press the calculate button, and it comes out. That's a huge, that is a huge planet, 15 times Earth size. And so here's a little summary of what your planet's like, and then the last slide is an artist's rendition of what that planet might look like. We don't have actual images of any planets, and then you can go back and pick another star to investigate. So that's a nice little interactive that steps students through the whole process of finding the average distance, the size, the whether it's in the habitable zone, and what the temperature is. There's so much information that we can get about the planet just from observing its brightness, the brightness drops of the stars. It's kind of amazing. Okay, so let's proceed to one other animation. There's an orbit animation. If you go to the Kepler Discoveries table, and I'll show you where that is in just a second, but there's a listing of all the planets. If you click on the name of the planet, for most of the, not all of them, the most recent one, another 1,000 planets has been discovered just this last May. Not discovered, but confirmed as planets. But if you just click on any of the earlier ones, we have this let's see. There's the discoveries table, and we'll click on one of those planets, and you can see that there's all the data on the table. But here's the animation that we have, and it shows a top view, and then that is actual data as the transit is happening. That's based on real Kepler data. Okay, those are, you know, the noisiness you can see there in the data. Then there's a way to increase the size of the font. There's the controls at the bottom. There's features like show the habitable zone of the planet. Now, that planet is very close to its star. It's nowhere near the habitable zone. You can show solar system orbits, which shows that the planet is really... Okay, and some of those lines might not show up on the screen here, but if you use the animation, these things show up. Then you can switch to a view from Earth. Rather than top view, go to a view from Earth, which that's a nice little transition there to understand how a planet going back and forth sideways is actually a planet going around the star. And then you can zoom in, zoom out with that control, and then you can control the speed as well, the speed of how fast it's going around. And it can slow down for the transits if you have that box checked. Okay, so this is a nice little orbit light curve interactive that is available on the Kepler website too. Okay, now to wind up here, and before I get to the question and answers, I would like to show the Kepler star wheels, and this is like a less than a minute movie. Okay, so let's just show that movie.
Download the star wheel and make one. It's very simple to do. For sturdiness, it's best to photocopy it onto a thick paper or glue it onto a file folder. Some kind of heavier paper would make it more sturdy. But one piece is the wheel itself, okay, and you just cut that disc out. And the other piece is the holder piece, which you have to fold actually along the bottom, and you fold it along the sides, okay, and then you tape along the sides, both sides, and that's all there is to making the holder. Scissors and tape is all you need.
Get my microphone back on here. Okay, I guess I didn't say exactly what Kepler star wheel is. It's a planisphere. It shows the image. It shows the sky as it is any time of day, any time of night. But this particular one, the Kepler star wheel, has the Kepler field of view on it, marked in the position that it is between Lyra and Cygnus. And it also has, this is one of the neatest things about it, is that it has all of the stars that are known to have planets, and for stars that are naked eye stars, okay, up to about magnitude 5. And there's green circles on the star wheel that indicate those. When I first made one of these star wheels, I just downloaded a listing of the exoplanets. And the first one that came up, the brightest one, was a magnitude 1 star in the constellation Gemini. And I thought, whoa, magnitude 1 star in the constellation Gemini? That's got to be Pollux. And it is. Pollux is the brightest star that is known to have an exoplanet at the moment. The brightest naked eye star, the brightest star from our perspective. Now, the star wheel was based on a thing called Sky Challenger, so this is another pretty short movie, not less than a minute. And this is the last movie that I have. So let me play that.
It's a Sky Challenger, and it's a planisphere, but it has 6 interchangeable disks. Okay. There is one that is for basic star finding. There's a wheel that has star brightnesses on it. In fact, this is the one with star brightnesses. You can see some magnitudes of stars written on this one. There's a wheel that shows the Native American constellations. That's a specialized wheel. And there's a wheel that has a binocular treasure hunt. It has objects marked on it that are in nebulae, star clusters, galaxies, and things like that, that you can see with binoculars.
Okay, let's get up the last set of slides, and I want to say one more thing about those Sky Challengers. There's my email address again. This is a picture of the Kepler homepage, and I just wanted to. I put red circles about the things that I've covered in this webinar. Things that I've been talking about is in the news section. The discoveries that Kepler made. If you look under news, you'll see it's kind of what was news at the time is now the history of the mission. Okay. Then there's the discoveries table, that next circle. See, let me get my pointer again. The discoveries table. And then all the other things that I was talking about is in the education section. So the transit tracks activity is under activities. The Kepler star wheels are there. And the simulations that I showed are under simulations. There's both the orreries, and there's a separate page for computer simulations. Now the star wheel that was just talking about, the Sky Challengers, I should say, were the original thing that the Kepler star wheels were modeled after. And Kepler star wheels were modeled after what's called Uncle Al's star wheels. And on a web page there are these different versions, these different types of wheels that you can put in. There's a Japanese version, English version, higher latitude. Southern Hemisphere, there's a Spanish version, a Portuguese version. And the original Sky Challenger wheels, though, were not available. They went out of print. But we now have them available as a do-it-yourself. You can make it yourself, and it fits the same kind of holder as in the Kepler star wheels. So that's something you might want to check out. Now, this is this is a reminder that before my time runs out, to paste all of the links that I had into the chat. Now, let me see if this works. I made a collection of all those links, and I'm wondering if that will make it into the chat. Okay. That is not all of them. So I might have to copy it more than once, or send it by email or something. Let's see. I'll figure that out. And I had so actually, this might be a good time. I have a number of more slides that are more about sort of mission results, light curves. Well, maybe I can step through these quickly. This is the first 5 planets that were discovered and their light curves. Notice that one of them is 4 times the size of Earth, but the rest of them are giant. Those are the easiest ones to find. The huge planets, they have the deepest light curve drops in brightness, and also the shortest number of days for their period. The more times it goes around, the easier it is for us to discover them. These are a plot of transiting planets that were discovered before Kepler. Okay, and it's a plot of the size of the planet relative to the orbital period. Notice that they're all clustered in the upper. They're the large planets with the short period. In the upper left here is the large planets with short period. So the Kepler planet candidates, soon after it was launched, it was discovering planets down in this region here. But over the period of the mission, which was 4 years, it found a bunch. This was the same chart as of 2013. And notice that there's still sort of the holy grail, or our goal is to find the Earth-sized planets in the habitable zone of the star, and there's still not many of those discovered. But a significant result of Kepler mission is that there are some in that region. Okay, so we know there are Earth-sized planets in the habitable zone of a star. Here's the sizes of some of those planets. This is an interesting chart. Now, all these images are also on the Kepler website and in the graphics area. This is interesting for a number of reasons. The most incredible thing, actually, is that these super Earth-sized planets, which are between 1.25 and 2 Earth radii in size, there's a lot of those in the Kepler field, and this is representative of the galaxy. And then there's these Neptune size. Okay. There are none of these super Earth size in our own solar system. Okay. Let me show you the latest version of that was as of May 2016, when over 1,200 planets were confirmed. This is the latest chart, and you can see that this is the sub-Neptune category. There's nothing like that in our solar system. And the super Earth category. Those are the most common planets in our galaxy. Turns out that's what Kepler has discovered. We don't even have that in our solar system. How did that happen? Why did that happen? It must be a fluke or something. Okay, I'm going to leave it at that and open up to questions, because I think we need to have a period of time for questions.
Thanks, Alan. Indeed. So now is the time. Put your questions into the chat, if you will. I think we've kept pretty much up to date with everything that was in there so far. We've found a couple of things that people were looking for. As my colleague Alberto said, Alan, we'll put all of the links that you've mentioned onto the same site where the recording of this webinar will be. That'll make it easy for people to find it.
Let me email that one to you. Let me email that to you. Just to make sure it's complete.
We'll pick it up from you afterwards.
Yeah.
And then meanwhile, I see we're starting to get some questions coming in, and then we're also going to go to Rosa as well too, but let's take a couple of questions first. Nuno, looks like our solar system isn't exactly typical. It's a comment. What do you think, Alan? Seems to be true.
Well, yes, that is kind of amazing. We don't have any super Earths, in the sense that we don't have any super Earths or these sub-Neptune. I call them mini Neptunes. We don't have any of those. So yes, the solar system is unique and unusual in that regard. Now, why that is, I don't know. Maybe it's just luck of the draw.
Presumably we won't be around long enough to actually find out. How long does Kepler go on for, Alan?
Oh, you know what? Thank you for asking that question, because it was a 4-year mission that was completed in 2012. It was launched in 2009 and finished its data collecting in 2012. Now, it finished it because it was equipped with 4 what are called reaction wheels that are like gyroscopes that create the extremely accurate pointing necessary for this mission to keep the telescope pointed. And it lost one of its reaction wheels actually after the first year of operation, but it only needed 3, so we were in good shape. But in 2012, it lost a second reaction wheel, and so that. Fortunately, it was near the end of at the end of our data collection period. But an amazing thing happened. They started looking at, the engineers and the scientists started looking at, well, can we make this, the telescope was in perfect condition, other than 2 reaction wheels down. And so they looked at, can we make this work with 2 reaction wheels? And what they came up with was, well, yes, we can, because if we look at only objects in the ecliptic of the solar system, the ecliptic plane, that is the plane that the Earth's orbit is in. So all the areas of the sky that are exactly opposite where the sun is with respect to the Earth. The reason why it could do that is because the main thing that was throwing the pointing off that needed to be corrected for was the solar wind. So they found that if you are pointing at an object that's opposite the sun, the solar wind will actually act as a neutralizing factor, and they only needed then 2 reaction wheels to accomplish very precise pointing. And so, Kepler mission is still going on now, except that it's the K2 mission. And its mission now is not only to discover planets, it still can discover planets, but it can only look for 88 days at a time. That's because it can't, when it goes around, it's in orbit around the sun, actually. So it can't look towards the sun. So it, you don't want to point something like this at the sun. Okay.
Two further questions, and I think we'll then switch to Rosa. From Alberto, what is the planet's orbit a star in a way that no transit is visible for us? Is it possible to deduce something by the gravity oscillations of a star? And in that case, what can and can't we know from that?
Okay, that's another very good question. And yes, that's a different technique. Kepler is using the transit technique, where the planet goes directly in front of the star and we look for drops in brightness. A technique that preceded that and still is used is the radial velocity technique, where you don't have to have a transit, but you look at the shifts in spectra, the red shift in spectra, to analyze the period of the star. It turns out that using that method, you can determine the mass of the star. Okay? You can get an estimate, well, at least an upper limit, or is it upper limit or lower limit, of the mass of the star, which Kepler cannot determine the mass of the star. Kepler can only determine the size, the physical size. So if we are able to observe a planet with Kepler to know its size and get a ground-based observation of, using radial velocity method, of its mass, then we actually can know the density of that planet and have an idea of what it's made of. So whether it's a rocky planet or a gaseous planet or a water planet, we can determine things like that.
Okay. Rosa has a question also from the audience in Marathon. Do we know how many of the super-Earths are in the habitable zone?
I don't know that on the top of my head. But there is a table, on the Discoveries table that's on the Kepler website, we have a link to the main data source, okay, the NASA exoplanet data center. And there you can adjust parameters for whatever size planet and whatever details that you're looking for, and you could probably determine, well, it wouldn't be easy because every star has a different habitable zone, but and I don't know anybody who's done that, actually. So good question, good project for somebody.
Sounds like a good project. Look, we're just about to run out of time, so I want to bring in Rosa. So can we switch on Rosa's camera and mic? Because she wants to tell us about a scenario which is available. So Rosa, you need to activate at your end your camera and microphone, because we've given you rights here. Yep, there we are. Over to you, Rosa.
Okay. I cannot see my face there, but I suppose you can hear. Can you see the audience here in Marathon?
Yes. Hi, Marathon.
Okay, good. So I will not turn the camera to me. It's okay if you see the participants. If you could put, please, the link to the scenario here, or share the scenario, that would be nice. Exactly. So it will take 2 or 3 minutes just to let you know that we decided to create a scenario very quickly to take this opportunity of having Alan with us. And we created quickly a scenario about exoplanets. It's a scenario, again, using the 5 inquiry phases. So in the Inspiring Science Education platform, you can see that in the orienting phase we have a nice movie and some challenging questions like what is the best experiment to find exoplanets, if it is possible to measure physical properties, and if the students would propose a new way to identify exoplanets. And again, as we know, Inspiring Science Education scenarios, we have all the problem-solving questions there. then again we have the hypothesis stage, where we invite the students to understand better and to make their own hypotheses on how can we find such planets and how to work best their own model for their own hypotheses and proposals. Again, we have some problem-solving questions. In the planning and investigation phase, we are using precisely one of the tools that Alan shared with us, so you're already acquainted with that. And again, we have some questions for the students to reflect on that. And some in the analysis and interpretation, we again are covering parts of the precious information that Alan shared with us and following exactly the material that they have developed for Kepler satellite. And finally, in the conclusion phase, we have some tips for them to finalize the lesson. So it's a simple scenario that we invite you to clone, explore, and change it the way you seem fit to use with your students for the next school year, or for those of you in the Southern Hemisphere during this school year still. So this is all from my part, Sally. I don't know if the audience here is willing to ask more questions to Alan. Anyone here would like to ask anything for our exo-alien Alan?
They've gone shy in marathon, have they?
Okay, I don't think so.
I think we're going to close it then. Thank you very much, Rosa. And thank you, everybody.
Thank you, Sally.
Thank you, everybody in Marathon, and everybody else, of course, who joined us this afternoon. But most of all, thank you very much, Alan. It's been really great. Thank you. And we've really enjoyed having you with us. Just to remind you all that we're looking for input to improve the ISE offer. Please don't forget our survey, which is always on the front page of the website. We also want to remind you that the recordings of these webinars, the series of 3, the previous 2 are already available, and this last one will be available shortly. So that's really all that I have for this afternoon. Just to remind you about our social media channels as well. Alan, thank you. You got up very early in the morning. I know it was very early, 7 o'clock for you. Thank you so much for your enthusiasm and, of course, your super expertise.
Thank you. I'm going to go have breakfast now.
We're all finished work here for the day in Belgium, and I think in Greece they're probably off for the rest of the evening as well. So thank you much, everybody. Thanks to my colleague Alberto for all the help, and bye-bye, everybody.